So, welcome to the first session of this course, Opamp Practical Application Design, Simulation and Implementation. So, today this is the first lecture, first doubt session for this course, which was like the lectures which we studied in week one. So, I will be discussing about the topics you studied in this week one, and then yeah, then we'll also solve the assignment questions. So, basically, the agenda for these doubt sessions will be I will write down this thing for you. Agenda for doubt session. So, in starting, we will be uh, doing a revision, a quick revision of whatever we will be learning in that particular week. So, there will be revision. After that, we will be taking doubts. Like if you have some doubts while you were going through those lectures or concepts, so we'll take those doubts and we'll try to solve that. And then we will be discussing about assignment assignment questions. And then in the end of the class, we will also solve some extra questions which I have designed so that extra questions which I have designed so that you can get intuitive feeling of what you are actually studying, and you can practice those concepts via those questions, and yeah, you can make your concepts more clear and more strong. So this will be the basic agenda for these doubt session classes. So today we'll be starting with the week one topics. So in week one, we so as you all know that in week one professor told about he just went through the integrated circuits and why ICs and all those are used and why there was a need for op amps. So yeah, we'll start with that only. So initially we talked about integrated circuits that we call also as ICs. Okay, integrated circuits. So what are these? These are miniaturized low cost electronics. So basically we are reducing the uh, size of the circuits. So that's why we are saying miniaturized low cost electronic circuits. These consist of passive and active components which are being fabricated in from which are being fabricated on a substrate, and the substrate we normally take as silicon. So these are fabricated on a substrate, and this substrate is silicon. Mostly we use silicon. Okay. These active components can be what? Like diodes, or we have seen transistors. And if you talk about passive components, then these are resistors and capacitors. Capacitors. Okay. Then why we need ICs? Then a question arises: why we need ICs? Since we talked about ICs, we came into these we came to learn this integrated circuits, but why we need those? So first of all, first thing, the important thing, that these are miniaturized. They are very small, so we can use that easily in our circuits. Like if we are designing a circuit where we have to integrate that circuit in a very sophisticated place or something, for variable sensors and all, then we can use these ICs. So these are miniaturized versions. And this miniaturization also helps in equipment density. Like we can use many density. We can use lots of we can use many passive and active components in these ICs, and we can increase their functionality as according to our requirements. Since we are producing these in batches, lots of like big bulks production in batches, so thus their cost also reduces, thus reducing cost. Okay, then they are reliable also because their packaging is very well designed, and they are very well packed. And then they have better functionality. Okay, their speed is also high, increased operating speed, increase operating speed. And also the power consumption in them is less. Okay, so we have two type of ICs. If you look about ICs, so we have two type of ICs. One is linear ICs, one are linear ICs, that what we use as what we will be looking into is op amps. And then there are digital ICs, which are like switching on off and on. So uh, these are used in computer and logic circuits. Okay, so here, as the name suggests, linear ICs, the input output relation is linear. Input and output relation is linear. Whereas in digital ICs, the input output, the output basically is on or off, on or off. Okay, so this act as a switch, we can say. On or off states are there. Hmm. So this then we talked about ICs. So if we just talk about how they are made, so these ICs are basically the substrate is of either silicon, glass, or plastic. Okay, and yeah, so but mostly we use 95% of the ICs are made of silicon because of their easy availability of the substrate. Then since we talked about ICs, and then based on ICs, using these ICs we can develop op amps. So now we'll talk about op amps. And then in this course we'll be talking about different applications, and yeah, different applications of op amps. We'll be talking about simulations using op amps, and we'll be also looking into some practical implementations of these op amp circuits, how we can practically implement them, and use use these op amps to realize some basic functionalities and all in our, and how these op amps can be used in our daily lives as a sensor. So now we will be talking about op amps. Op amps. Okay, so if you talk about the advantages, so since initially we were using only transistors, but now by the incoming of these ICs, the concept of ICs, integrated circuits, we were able to use lots of transistors in a very small place. So based on that we realized these op amps. So if you talk about the advantages, so initially we were using JFETs, FETs, etc. But now, by the combination of these, we can realize op amps, and how these op amps are having advantages over these transistors. Advantages of op amps. So why we came for op amps? So since so the reason is like they are using less power, then cost is also less, cost less, since we are it's a mass production, and then they are more compact, then more reliable also. We can obtain higher gains, and then easy design. Okay, so now since we have started a discussion on Opamp, so let's look into what are the ideal behavior of this Opamp. Uh, the ideal Opamp. So what are all the characteristics of these ideal Opamp? So first characteristics, if you look about, that is the infinite voltage gain. Infinite voltage gain. So for an ideal op amp, if you look into, so the gain it provides is ideal. It's very high. So if we are applying if we are applying uh, 2 voltage at the input terminal of the op amp, then the gain will be almost tending to infinity. But in reality, if we see, it is near to 2,50,000. In reality, this is the gain, open loop gain. But ideal case, we are the open loop gain of the op amp is infinite. Then the second characteristics is infinite input resistance. The op amp should have infinite input resistance. Okay, so that this will avoid the loading effect. This is done because this will avoid loading. But in again, if we talk about real case, in reality, this is approximately in 10 to the 12 ohms range. This is also very high, but still there is some value to this input impedance. Then if we talk about output impedance, so that is zero. So this will not load any other circuit, not load the other circuits. Okay, so after this, after so yeah, and then also they have infinite, they are infinitely fast. That is they have infinite bandwidth. Okay, but in practical cases, if we talk about practically, they are having so it depends. They can have, I think, 1 megahertz of bandwidth, or they can have like even greater bandwidths up to 4 to 5 megahertz also, and they can have less bandwidths also, like up to 100 kilohertz or something. So it varies, this bandwidth practically. So then so we also learned that when an op amp is connected in a negative feedback network. So let's say this is the op-amp network, and if we attached a negative feedback to this op-amp, then it follows a concept of virtual short concept, where in this thing, this V1 voltage, the voltage at the inverting side of the op-amp, that is V1, is equal to the voltage at the um, non-inverting side of the op-amp. Okay, Then we also learned about single-ended output and of the op amp. We also learned about single-ended output and double-ended output. So this is like this. This is double-ended output and this is having single-ended output. So now if we talk about the feedbacks in op amp, we can have either positive feedback or negative feedback. But first of all, why we need feedback? So we know that the gain of the op amp is very high. So that is like so if we say the open loop gain of op amp, open loop gain of op amp is approximately, let's say, 200,000. So so if we are amplifying a signal, so we don't want this much of amplification. We want to first of all control this amplification factor also, and the second is first thing is we have to control this amplification amplification, and the second thing is that also we don't need this much of gain. This is very high. So that's why we introduce a negative feedback. So if we talked about an op amp plus, if we connect the negative inverting terminal of the op amp to the output, and we are giving some input here, then this is basically a unity gain amplifier. So here it is providing a gain of 1. So whatever input we are giving, it is coming out as an output. So we can change this gain also by introducing one register in the feedback. That also we can do. So this is a type of example of negative feedback. But we also use positive feedbacks, like in oscillation circuits, or when we are going for non-linear applications of op amp. We will be looking in future lectures what is these non-linear uh, applications are. What are these non-linear applications for the op amps? Non-linear applications for the op amp. These are oscillations, yeah. So in this the circuit in positive feedback, simply if we are giving input to the non-inverting side, so we are giving output from the non-inverting side of the op amp, V naught. So this is the case of positive feedback. So in this case, the output will keep on increasing like this. So yeah, so this was about the feedbacks. Now we have since we have talked about feedbacks in op amps, the ideal what are the ideal behavior of the op amps. Now we will look into the op amp characteristics. Op amp characteristics. So we have various characteristics for op amps, like open loop gain. Then we have input impedance. Then we have also output impedance. Then bandwidth of the op amp. Then input offset voltage. Then we have input bias current. So these are like some of the characteristics of the op amp, where these are all practical for practical op amps. So in real life, when we talk about Opamp, the Opamp seizes its behavior from the idealistic behavior, and it shows some practical problems like which we'll be looking into these Opamp characteristics. So we have talked about open loop gain, input impedance, output impedance, even bandwidth also. So if we talk about because we saw that open loop gain is not ideally infinite. It is like normally 200,000 or something in near to that range. Then we talked about input impedance that is in mega ohms or giga ohms. Sometimes that is not infinite. Output impedance, it is there like but it's not zero completely. Some value is there like 50 ohms or something depending on the output current. Then we have also limited bandwidth. We don't have a bandwidth till infinity. So then, but these two concepts are new, like input offset voltage and input bias current. So if we talk about input offset voltage, so input offset voltage. So yeah, so input offset voltage. If we talk about, so this is the volt. So even if we don't apply anything at the input of the op amp, so the input signal we input is zero. Then also the op amp will show some output will be there. So this is because of the some differential voltage we so some differential voltage at the input of the op amp. So that voltage, when we apply zero input at the input terminals of the op amp, the output voltage is equal is proportional, we can say proportional to the offset voltage. So this is because of the offset which is this op amp is having. If we talk about now input bias current, so the bias current is given by IB1 plus IB2 by 2. And what are these IB1 and IB2? So IB1 is we can assume IB1 is to be the current entering into the inverting in terminal of the op amp, and IB2 is the current uh, going into the non-inverting terminal of the op amp. So based on that, if since so there will be a drop in the input terminals of the op amp, and we'll get some output. And we also have input of this offset current also, that OIOS. It is given by modulus of IB1 minus IB2, and this its value is normally 20 to 60 nanoampere. So if we talk about the definition of this input bias current, so that is basically um, if we are applying if we are applying equal DC currents to the two inputs of the op amp, then output voltage must be zero. Okay, but voltage must be zero. But but practically, if we see practically, there exists some voltage at the output. So to make this zero, to make this output zero, two input currents two input currents are made to differ by a small amount. This difference in current if this difference is offset current. So we are saying when we apply equal currents to both of these negative and positive terminal of the op amp, then since they are equal, but still then also there will be some output. But ideally we should get zero. We should get output as zero, but still there is some output. So why it is because of the bias currents which are in the negative terminal and the positive terminal of the op amp. So if we apply some difference, so if we apply input currents in some difference, that is this IB1 minus IB2, then that current will make this output to go to zero. So that is what offset current is all about. These input current are this input bias and input offset current. Input offset current depends on temperature. So this is important. So then we also there is a one there is like the differential mode gain. There is a concept of differential mode gain in op amps, that is AD. We call it as AD. So this when the output of the op amp is given by AD V1 minus V2. So this is the differential gain. Normally the output of the op amp is gained by the amplification due to the differential gain AD of the op amp and the differential voltage VD, that is V1 minus V2 plus ACM into VC. So this ACM is the common mode gain of op amp. Okay, and this VC is the common mode voltage, that is VC equals to V1 plus V2 by 2. So normally if we talk about ideal so ideal op amp will behave ideal op amp will be having CMRR as infinite. So what is CMRR? CMRR is the common mode rejection ratio. So this is given by CMRR equals to AD by AC. So it shows that whenever we are giving some single-ended input to the op amp, we want to amplify difference of the input voltage, then this AD, the differential gain, comes into picture. But normally the noise in the op amp is common to both the terminals. But so these are the noise which is being entered in here and here also. So these are common to both the op amps. But ideally it should reject these noise because these are common to both the terminals, but practically it does not do that. So there is some gain because of these noise voltages also. That is what we that because of noise, this output voltage of the op amp is basically AC into the VC, the common mode voltage, that is the volt, that is this V1 plus V2 by 2. So that's why like this, instead of going to infinity, it is having some constant values, some finite value. So that's why the output of the op amp is given by this equation, V naught equals to AdVd plus ACM Vc, where Ad is the differential gain which we want, and ACM Vc is the uh, ACM Vc is the common mode voltage and the common mode gain for the op amp. So after this, normally, and one more thing, this CMRR, we give CMRR as equals to 20 log AD by AC, AD by ACM. Okay, this is there. So it is normally given in dB scale. So now then, if we look more into this bias current concept, so how it is affecting the output and all. So we will see. I'll just add some pages here. Pages. Six. Huh. So how do input bias current, input bias current IB1 and IB2 affect amplifier operation? So we'll see how this bias current is affecting the output of the op amp. So if we have an op amp like this, having some negative feedback with resistor R2, this is R1, this is the input we are giving, and this is the current entering from the non-inverting terminal is IB2. And yes, and this is IB1, the current entering into the inverting terminal of the op amp, V0. This is V0, and this is, let's say, I2, this is I1. So ideally we want, so the if we talk about KCL at this node A, KCL at node A, then I1 equals to I2 plus IB1. Okay, so I1 is what? Since this is virtual short, so this is grounded, so this will be also grounded. So it will be V in by R1. Okay, and what will be I2? I2 will be, okay, if we go in another form, let's say I1. So what is I2? I2 is I1 minus IB1. Okay, and what is I1? So this is node A. So let's say this is V minus here. The voltage here at node A is V minus. So it is what? I1 is V in minus V minus divided by R1. Okay, but since this is virtual short, so this will be grounded. So it is V in by R1. And what is I2? I2 is V minus minus V naught by R2. This is 0. So it will be minus V naught by R2. Okay, so V naught is given by, if we substitute this in this equation, then V naught is given by equals to minus R2 by R1 V in plus R2 IB1. So we saw that because of the bias current, this is the effect of bias current. Okay, so this is the effect of bias current, and this is what we wanted. So the gain due to inverting terminal, inverting amplifier, this is we wanted response, and this extra thing we are getting here. So this we want to avoid. This is because of the bias current. This we don't need. So how we can remove the bias effect of the bias current from the output of the op amp? So if we see how to compensate for the effect due to bias current, effect due to bias current. So the circuit I will be so let's say we are not we just for the time being we are not giving any input voltage. We are just talking about the effect of the bias current at the output. So this we saw earlier, R2, R1. We input voltage we have grounded, and now we are connecting one resistor here, that is R. We don't know the value of this R. Let's say it is R3. So this is the current IB2 entering from here. This is the current IB1. This is I2. Okay. So now, if we talk about I1, what will be I1? So this is what we saw in I1 was I1 was the current from here, I1 Vin minus V1 by R1. So Vin is 0, but V minus here in this case will be IB2 IB2 R3. Okay, this is IB2 R3 divided by R1 minus, this is the drop from here to here. So this will be a minus voltage there, minus of minus. So it will be IB2 R3 by R1. Okay, then I2 will be I2 equals to V minus minus V naught. This is V naught divided by R2. So it will be minus IB2 R3 minus V naught by R2. This is another equation. So if we substitute this equation in I1 equals to I2 plus IB1, that we saw earlier also. So it will be I2 will be equals to I1 minus IB1. So this will be IB2 R3 divided by R1 equals to minus IB2 R3 divided by R2 minus V0 by R2 plus IB2. Okay, so if we solve this equation, we will get IB2 R3 1 by R1 plus 1 by R2 equals to minus V0 by R2 plus IB1. So since we don't want any output voltage from these bias currents, so this we will assume as 0. So then what will happen? So this should be equal to IB1. That means if assuming IB1 approximately equal to IB2, then R3 will be the parallel combination of R1 parallel R2. So this is the assumption we made, and this is the result we got. So R3 equals to R1 parallel to R2. That will help in compensating. So this R3 will become R1 parallel R2. So this will help in removing the effect of bias current from the output. Okay. So then we have other Opamp characteristics like thermal drift. That, as the name suggests, this is the drift due to the temperature variation in temperature. So this is variation in Opamp characteristics. Opamp characteristics due to temperature. Okay, thermal drift. Then we have also output voltage swing. Output voltage swing. So output voltage swing is basically since we are giving, let's say, plus minus V set to the input to the power supply of the op amp, but since we are giving this, so we expect this the output should be also varying from plus V set to minus V set. But instead of this does not happen. This is ideal behavior. It varies from plus V set minus some V offset V voltage, or let's say swing voltage, minus V set minus V swing. Okay, so it varies between this. This is real behavior, real slash practical. Practical behavior. Hmm. So now, we also talked about earlier we talked about CMRR. So I forgot to tell you that CMRR, this is normally 90 dB to 110 dB for a practical op-amp. So this is considered to be a good CMRR. This 90 dB to 110 dB. If it is going lower than this, then there's like then it will start showing more impracticalities in its output characteristics. So CMRR of 90 and 110 dB is good. Then there is one PSRR also, that is power supply rejection ratio. PSRR, that is power supply rejection ratio. So it is also given in dB scale, and it shows like while we are giving power to the op amp, then there is a chance of noise entering through that when we are using that op amp in high frequencies. So to avoid that, there is some power supply rejection ratio of these op amp. So it should also be high. So for example, if we talk about this PSRR, let's say PSRR of an op amp is 90 dB, 96 dB, let's say. Fine. Then we are giving 12 volt supply, 12 volt supply to the op amp. Hmm. And a 100 millivolt ripple, that is basically, we can say, noise, 100 ripple at 120 hertz entered the op amp. Then how much it will be able to uh, remove this ripple from entering into the op amp? So if we talk about the formula for this, that is 20 log of PSRR equals to 96 we have been given. So this is PSRR. Yeah. So PSRR R equals to 96 10 to the power 96 by 20, which is given by 63000. So this means that the ripple seen by the input of the op amp will be reduced by a factor of 63000. This what does it means, PSRR, power supply rejection ratio. So let's say if we are giving 100 millivolt, so if a 100 millivolt ripple came, that will be reduced by 63,000. So we will see only 1.6 microvolt of ripple at the output, at yeah, of the ripple at the input, sorry, at the input of the op amp. Okay. Then there is also one more characteristic that is important characteristics also, that is transient response of the op amp. Transient response of the op amp. So this gives an idea how fast our op amp is. How fast our op amp is. Okay. Here one more concept comes, that is slew rate. Slew rate, that is given by volt per microseconds. So for example, if we have, let's say, 10 kilohertz of signal, and that is 10 volt peak sine wave we are giving. So if we talk about the output of the rate of change of the output of the op amp, that will be 10 sine 2 pi ft, which is equals to 0.63 volt per microseconds. and we assume that this op amp is having 0.5 volt per microseconds of slew rate. So but the signal which we gave, and we also assume that the gain of this op amp is, let's say, 1. So this is 10a, so this is one like this. So but we get the maximum rate of this op amp as 0.63 volt per microsecond. So that means like the slew rate which this op amp wants is more than what it is actually having. So because of that, the output of the op amp will be distorted. So if you are giving a signal like this sinusoidal signal, so in reality it will not be able to achieve the speed of this input signal because it is very fast. So in reality it will be like this, a kind of triangular wave which we call as distorted wave. This is the input wave which we were trying to give, input wave, and this is the distorted wave which we will get at the output. So this is how the slew rate limits the output of the op amp. I will add more people. So yeah, we then then after that, after the op amp characteristics, in the next lecture, next video, we talked about filters also. So these filters, so we can realize these filters by using op amp. So what are filters? Basically, filters can either pass. We can say it passes some set of frequency, passes some set of frequency, the same time rejecting some set of frequency. So based on this, we have passive filters also, and we have active filters also. So these active filters, they use op amps, which we'll be seeing after some time. Passive filters, they use R and C circuits, the combination of R and C, or they can use also RC, RL, or LC circuits also. Okay, so the advantages of using this active filters, advantage of using active filters. It is, so we can adjust the gain of the op amp, or we can adjust the gain of these filters based on our requirements. So gain can be adjustable. Gain is adjustable. Gain is adjustable. So there is also no loading problem, as we saw. Like there is a high input impedance of the op amp, so no loading problem. Okay. And then these are also cost effective. So we have four basic category of op amps. Four basic category of op amps. Okay. So these are, first one is low pass, second one is high pass, third one is band pass, and fourth one is band reject. We also say notch filter. So now we'll talk about each and every type of filter. So we'll start with low pass filter. Low pass filter. Hmm. So if we talk about the response of this low pass filter, we will get like this for an op amp. So here this is 0 dB and this is like the cutoff frequency of this op amp, or we can say this filter. This is minus 20 dB per decade roll off rate, which we call as roll off rate. Okay, so this is then this is minus 3 dB at cutoff frequency, and then it is decreasing. So till cutoff frequency, we call this band of frequencies to be the bandwidth of the op amp or bandwidth of the filter. But ideally, we need, this is the practical response of the low pass filter. But ideally, we have seen that low pass filter looks like this. So it is like allowing all the frequencies below cutoff frequency, and it is rejecting all the frequencies above FC. So this is gain. This is one. Okay. So using passive components, we can realize this low pass filter as the combination of RC circuit like this. If we take the output of um, this filter, this is the input, this is the output, this is R and C. If we take output across the capacitor, then we can get the response as we have seen here. So how if we just analyze that, this is like for high frequencies, this capacitor will be acting as infinite. Uh, uh, so it will be acting as a short circuit. This capacitor will be acting as a short circuit element in high frequency. At low frequency, this capacitor will act as open circuit. So this is so the output will be V naught, will be in this case will be it will be 0. Here in this case it will be equal to the input voltage supplied. So by this way we will get the response of the low pass filter. Okay. Now if we want to realize this using op amp, so we will say first order low pass filter. First order low pass filter. So how we will see? I will see how we can realize this using an op amp. So we will just use this passive component, that is combination of R and C. This is the input, and after this we are connecting one op amp in unity gain amplification form. Okay, so this is V output finally. So what will happen? This is acting as low pass filter, and this is providing gain of 1, but at the same time it is avoiding loading, because the input impedance is very high, very high of this yeah, the op amp. So that's why it is avoiding any loading effect. But there is one disadvantage of this circuit, is that we are not able to get variable gain is not possible in this circuit. So now in order to get the variable gain, so we got the intermediate voltage, that is the output of the this low pass filter here, and it was providing a gain of 1, and it was finally giving the output V naught. At the same time, it was avoiding loading effect. But then, in order to get variable gain, if the case is there, like where the input voltage is very less, and we have to increase the voltage of uh, the output voltage we got from this RC filter, then for that case, we'll use a gain amplifier instead of this buffer. We call this unity gain amplifier also as a buffer. Now we'll talk about variable gain amplifier. So this is active low pass filter with amplification. With amplification. Okay. So we will use same RC network R and C. This will be we'll be adding a negative feedback to this Opamp. This is R2. This is R1. So here low frequency component is coming. Here high frequency component going. We are supplying V input from this side. Okay, we are getting V output. But now in this case, the gain will be, since this is the non-inverting amplifier. So the gain we will get is 1 by R2 by R1 plus R2 by R1. So this is the DC gain. DC gain. Because we are applying gain to this low frequency signals, that is the DC gain which we'll be getting. So the overall gain, the AC gain of this amplifier will be V naught by V input, which is given by V naught by V input is given by A divided by 1 plus F by FC square under root. So this is the DC gain which we talked about in this line, and then this F is the frequency for which we are calculating the gain, and FC is the cutoff frequency. So F is basically frequency of input signal, and FC is frequency of cutoff signal, cutoff frequency of cutoff, we can say cutoff frequency of this RC filter, that is given by FC is given by 1 by 2 pi RC. Okay, FC 1 by 2 pi RC. Now we can also use second order. So since we talked about first order low pass filter, we can also use second order low pass filter. Second order low pass filter. Okay. So here, since we were getting a roll off of minus 20 dB per decade, in case of this is gain, we talk about this is frequency. So we are getting minus 20 dB per decade of roll off frequency in this case. That was for first order. But instead of that, in second order, we will get a roll off of minus 40 dB per decade. So this will be more nearer to the ideal characteristics of the op-amp. That is the gain like this. This is the ideal behavior. Ideal. This is second order. second order low pass filter. So if we will keep on increasing the order of this filter, low pass filter, then we will be increasing the steepness, or we can say increasing the slope of this, or we can say decreasing the, will be able to decreasing the slope of this roll off region. Okay. And we can approach towards ideality, but actually with everything there is a trade-off, so we cannot keep on increasing the order of the low pass filter, so as more components will be involved and the complexity of the circuit will also increase. So that's why we'll have to like limit ourselves to some balanced trade-off between both of them, the roll off and the complexity of the circuit. So if we talk about second order filter, then it is a resistor. So we are giving negative feedback to this op-amp, and we are using two capacitors here. C1, this is C2, this is R3, this is R4. Okay, this is V input, this is V output. So the gain, we know the DC gain of this op-amp is 1 plus R2 by R1. The cutoff frequency is 1 upon 2 pi under root R3 R4 C1 C2. So this is about the second order low pass filter. So as we talked about high order filters, which can increase the slope of the roll off region, this roll off region. So how we can achieve that? So if we will cascade this voltage gain amplifier, cascade voltage gain, or in order to increase the gain of the op amp, so we can cascade these op amps together, or these active filters together, so that let's say the gain of this is 10, this is 32, this is 100, this is 20 dB, 30 dB, and 40 dB. These are the gains. So the overall gain will be 10 into 32 into 100, that is 32,000. In terms of dB, we will see it as 20 plus 30 plus 40, that is 90 dB. So this is in order to increase the gain of the op amps, we can cascade them together, and it will look like this. This is the RC circuit, op amp, feedback. This is R2, this is R1, RC circuit. Then we can again attach one more RC circuit, an op amp. So it is like this, R1, R2, and we can keep on doing this. So this is equivalent. Okay. Now we also after this, now we'll talk about high pass filter. Second is high pass filter. High pass filter. Okay, so if we want to realize this high pass filter using passive circuit, then we have this capacitor here, this resistance here, this is V input, this is V output. So the characteristics of this will be like this. This is the cutoff. After this, it will be this is pass band, pass band. Okay. This is gain. This is 0 dB. This is almost minus 3 dB. This is minus 20 dB per decade of slope. And again the frequency of this is, again the cutoff frequency of this is given by 1 by 2 pi RC. But if we talk about the ideal behavior, it is something like this. This is pass band here, pass band. This is gain. Okay. This is frequency, cutoff frequency. So now again, if you want to realize this passive filter using active filters, that is using op amps, then again we can use a buffer, or we can say unity gain amplifier, which is again something like this. We are using this. We are giving this input to the output, V output. This is V input. This is C. This is R. All the high frequencies will come here. Low frequencies will go there. This is unity gain amplifier. Okay, so this is first order high pass filter, HPF. But again the problem is that we cannot have variable gain here in this case. Variable gain. One more one more interesting thing to observe in this high pass filter is that this op amp, if we talk about this op amp, its inherent characteristics is often this, of an open, like low, or of an low pass filter. So we have seen that normally the open loop characteristics of an op amp looks like this. That is a kind of a low pass filter. But instead of that, we are realizing here a high pass filter. We are realizing here a high pass filter. So in order to but if this cutoff, let's say this is FC1, this is FC2. So if FC1 is less than FC2, then what will happen to the characteristics of this op amp? It will look like this. This is FC1, this is FC2. So we will get basically a band reject filter. But if FC1, we normally keep FC1 greater than FC2. So what happens? This is like, and we cannot in this case one more thing is there. Since the FC2 is more than FC1, and we are using this op amp more than its cutoff, like we are using this op amp, uh, this is FC1. So we are using this op amp as a, so we are using this op amp for like high frequencies which are higher than FC1. So it will, the gain of this frequency is above FC1. It will not be able to amplify those frequencies. So the gain will be less than 1. See, we cannot use this op amp in this configuration. We'll have to use in this configuration. So normally if we realize a high pass filter using an op amp, we will get a band pass filter, something like this. So this is the FC1, the cutoff frequency of the open loop of the op amp, and this is the cutoff frequency of the filter which we realize. So normally the high pass filters using op amps looks like a band pass filter. Band pass filter. Okay. So it is like this. Now if you want to realize with variable, with the amplification factor or variable gain, so first order high pass filter with variable, with amplification, we can say with amplification, with amplification. So it will be again that capacitor and resistor given to the non-inverting terminal of the op-amp. Then we are having one resistor here. This is R2, this is R1, this is output voltage, this is input voltage. So this is what? High pass filter. This is what? Non-inverting. This is non-inverting amplifier. Okay, so the voltage gain of this high pass filter here, it is given by voltage gain equals to V naught by V in, which is the DC gain provided by the this circuit, that is AF into F by FC divided by under root 1 plus F by FC का square. So AF into F. So if we just if we also if you want to analyze this thing, this expression, then for the, let's say for f equals to 0, that is low frequency, then this V naught by V in also becomes 0, because denominator becomes 0, because the numerator becomes 0. This is for f equals to 0, that is low frequency, low frequency. Okay, so for high frequency, this will be, the gain will be AF for f tends to infinity. So if we talk about that, so then this will be yeah, so ff will be cancelled out 1 by f. So yeah, we'll get some gain, some constant gain we'll get. Gain will be there for f tends to infinity. Now after this, now we will talk about band pass filters. So band pass filters are basically one high pass filter. We are using amplification and we are getting low pass filter from that. This is V output, this is V input. So in this case, FC1 should be less than FC2 to make it band pass filter. Okay, so FC1 is something like this. FC1, this is FC2. So this will make this as FC1 is here, FC2 is here, something like this. Okay. So similarly, we can also go for band reject filter. Band reject filter. Here in this case, the characteristics will be looking like this. Normally we achieve here a notch filter like this. This is a notch filter. So we have to remove one particular frequency or something, or we have to remove some band, then this is the characteristics. And we can simply again use the combination of low pass and high pass filter like this. So this circuit which I am right now it's drawing, this the part is the low pass filter. So this is R, this is C. Okay, here we are getting this, and at the bottom of the circuit it is high pass filter as we saw earlier. This plus, so both of them we are applying one buffer to avoid any loading. Then finally we are adding these two signals and giving it to a summer amplifier. This minus plus, this is our So this is V output. So this is summer amplifier. This is high pass filter, and this is low pass filter. This is V input. So in this case, if FC2, that is, let's say this is FC1, this is FC2. So earlier for band pass filter, we saw FC2 should be greater than FC1. In this case, FC1, FC2 should be less than FC1. Then in that case, if this is FC2, this is FC1, FC2. So FC2 was okay. Uh, so FC2 in this case, okay, wait, just for avoiding confusion, this is FC2, this is FC1. So yeah, FC2 should be less than FC1. So FC2 is the low pass filter frequency, that it will be like this, and FC1 is high pass filter cutoff frequency. So this will be like this. So if we'll make it more closer, then this will act as a notch filter like this. This is almost FC2, this is FC1. Okay, it will be like this. So this was all about filters. Then we also talked about oscillators. Oscillators, as in further weeks, we'll be talking about them in more detail. So just here I will be giving a brief overview of this oscillators. So oscillators are based on Barkhausen criteria, which says that modulus of A beta should be equal to 1. That is basically the feedback network, which and one more thing, these oscillators are working in positive feedback circuit, positive feedback network. So the feedback which you are giving from the positive feedback, the phase of that should add up to 0 degree. The phase of that positive feedback and the phase of the main circuit, it should add up to the 0 degree. So that's why this Barkhausen criteria is given. So if mod A beta is greater than 1, so we will get something like this. Our frequency, our oscillations will keep on increasing. If mod A beta is equal to 1, then our output frequency will be constant. The amplitude will be constant like this. And if it will be mod A beta less than 1, then it will be decreasing. So initially these oscillators are being run in this condition, mod A beta greater than 1. So once they start increasing their oscillations, increasing the amplitude of their oscillations, then we slowly, with the help of the feedback, we make them run in this condition, that is mod A beta equals to 1. So then the oscillation which they achieve, the amplitude of the oscillation they achieve, they sustain that amplitude, and they keep on oscillating. So in this we have like for low frequencies we have RC phase shift circuits, we have Vein bridge circuits. Then for high frequency we have tank circuits, high frequency LC tank circuits. Then in that we have Hartley oscillator, we have then Colpit oscillator. So based on the frequency requirements, we can realize these circuits either RC types of circuits or then LC tank circuits. Then in the end of this week, or the week one, we also talk about the loading effect. We did some experiments showing some loading effect. uh, so for that, we consider one voltage divider circuit. This is the input voltage which we were giving, and we wanted to measure the output voltage from this resistor. This is R2, this is R1. So if we will use a configuration of op amp like this, we have this voltage divider, and across this we use one inverting amplifier. Then we can see this is R1, this is R2, this is R, this is R. Okay, so what will happen in order to measure this voltage, the output voltage from this R2? Then since we wanted the current to enter through this path, but instead of that it will distribute to this part also. So I, which was being coming from the R1 side, that is from the source, I was coming, but here it will get diverted into two paths, I1 and I2. So this is causing loading. This I1 is causing loading. So this is not good. So this we want to avoid this thing, loading effect here. So instead of this circuit, what we can do? So to avoid loading here, we used again we this is R2, this is R1. We use buffer instead of the we use a non-inverting terminal amplifier instead of the inverting terminal. We not, and we can change this gain of this amplifier. And but here in this case, if you are giving some I here, then most of the I, approximately this will be I2 will be approximately equal to I, because only some bias current will be there here, which is very less, very less. Okay, so this will not affect the measuring of the voltage across R2. So that's why this will help in avoiding the loading effect by using a non-inverting configuration. Also, one more solution is there. Another solution for this is that we can use one buffer instead of this. After that, we can use inverting amplifier. So this is R1, this is R2, this is V input, and we have buffer here R. This is V output. So in this case, so yeah, in this case, this buffer is avoiding loading effect, avoiding loading effect. Okay, so yeah, so this was there in this this week, and then I will discuss about some assignment questions. So I will give you basic hints on how to solve these assignment questions. So based on that, so for the first question which is here, so first of all, yeah, we completed what was being taught in the week one lecture, and then now we will be solving some of the assignment questions. We will be seeing about some of the assignment questions. So yeah, so first one was, which of the following electrical characteristics is not exhibited by an ideal op amp? So they are saying which is the electrical characteristics which is not exhibited by an ideal op amp. So we have talked about like many things. So here like we talk about voltage gain also, bandwidth also, output resistance, slew rate also. So you should tell this answer by simply thinking like what will do, what this characteristics will do. The characteristics explained like mentioned here. So infinite voltage gain. Okay, we need if it is ideal characteristics on op amp is like it is providing infinite voltage gain, then based on that will it be beneficial for us? And if it is if giving infinite bandwidth, then I think this is also good because we can able to amplify frequency from any value. Like higher frequency also we can amplify a lower frequency. There is no limitation of the bandwidth. So then if we talk about output resistance, so they are saying there it is infinite output resistance. So will it affect any loading? Will it like produce any loading effect on the circuit attached to the output of this op amp? So then there is a case of infinite slew rate. So how this will affect if it is not infinite? So you will have to look like this in this question one. Then this is an ideal op amp. Then if we talk about second question, an ideal op amp requires infinite bandwidth because. So they are saying now the ideal op amp it requires infinite bandwidth, but why? So there are some signals can be amplified without attenuation. Okay. Output common mode noise voltage is zero. Output voltage occurs simultaneously with input voltage changes. Output output can drive infinite number of device. So these are the things. So you will have to see if the ideal characteristics of the op amp is of having infinite bandwidth, then how it can help that, how it can help us. So which of the answer below answers is correct? This also second is also straightforward. First is also straightforward. Then third. So the ideal op amp has infinite voltage gain because the ideal op amp has infinite voltage gain because to control the output voltage, to obtain finite output voltage, to receive zero noise output voltage, none of the mentioned. So we have seen infinite voltage gain. So we have seen this to be infinite. So then we also know V naught, the output of the op amp is AdVd, that is V1 minus V2. So if this is open loop gain, let's say we haven't connected anything. So what will happen? V naught divided by A equals to V1 minus V2. So if this is tends to infinity, this whole will tends to zero. That will imply V1 equals to V2. So one more thing like this is based on the infinite voltage gain. It is getting we are getting the concept of virtual short here. So that is one thing. So using this virtual short, we can we use this virtual short concept in negative feedback circuit when we use negative feedback. So since these both are equal, so we can so based on that can we achieve some of the properties here mentioned. So you'll have to think like that. Then the next question is find the output voltage of an ideal op amp. V1 and V2 are the two input voltages, and A is the gain. So we have V1 here, V2 here. What will be the V output? So you already know this is very simple. Which of the following is a differential type of amplifier? So they are talking about differential type of amplifier. So you first basically you should know what are these amplifiers mentioned here. So isolation amplifier we talked about, that is the buffer. This is minus, this is plus, this is the input which we give. Then instrumentational amplifier is one resistor in there which is being which controls the gain of this op amp. We give V1 and V2 here. So basically this is an IC. It consists of three op amps inside it. Okay, then there is a negative feedback amplifier. You know what how it looks like. Then based on that, what will be the answer for this question? You can solve that. So differential basically means for the amplifiers you are giving an op-amp and input voltage which is and the op-amp which is being fed with these input voltage, that is basically amplifying the difference of the input given. So based on that you have to answer this. Then there is a question: an amplifier has its FL and FH frequencies at 1000 Hz and 500 kHz respectively. So they are saying FL is 1000 low lower frequency and FH is 500 kilohertz, and they are saying open loop gain is 200. So then they are saying a feedback network with feedback factor beta is given as 0.8 is connected to the amplifier. Find the new lower and upper cutoff frequencies. So this is looking like this, something like this. This is 1000 hertz, this is 500 kilohertz. Okay. So you can also say that this has been achieved using high pass filter, and this thing has been achieved using low pass filter. So then using the formula for low pass filter, that is A equals to ADC AF we have mentioned F by that is sorry F A upon 1 plus F by FC ka square under root, and for this equation A equals to AF F by FC divided by 1 plus F by FC ka square under root. Okay, so using these two things, uh, using these two things, you can able to derive like the change in frequency at the lower frequency and the higher frequencies, how it will be affected uh, if we will introduce a feedback factor of 0.8 in that. So you will have to use these two equations for low pass filter and high pass filter. So then there is a question: op-amp with slew rate 10 volt per microseconds and gain of 40 dB. If this amplifier must faithfully amplify sinusoidal signals from DC to 20 kHz. So they are saying maximum frequency which can be amplified is 20 kHz without introducing any slew rate induced distortion. Then input signal level must not exceed. So they are saying what will be the input of this thing if the maximum frequency of the output can be 20 kHz. So they have given slew rate also and the gain also. So we know 40 dB, that is 20 log V naught by V in. This is the gain given of this op amp. So based on that, V naught by V in equals to 100. That is the gain, the closed loop gain of this op amp is there. So if we talk about dV naught by dt, that is V input into A. This was A, and yeah, that is into omega 2 pi f. This is the maximum rate of this op amp which we can achieve, and it has been given, it is equals to this slew rate. This is 10, it is given 10 volt per microseconds. Okay, and V in we don't know, A we know 100, frequency maximum we know 20k, so we can get a V in from here. Then our next question says that a tuned amplifier has a peak output at 2 megahertz and quality factor 50. So it is given peak, if peak is 2 megahertz, quality factor is 50. The bandwidth and 3 dB frequency shall be what values respectively. So for this, the Q is given by peak frequency divided by bandwidth. Okay, and if we see the quality graph is something like this. This is the bandwidth. So here this is fc, this is fc plus beta by 2, which is equals to f2, and this is f1 equals to fc minus beta by 2. So this bandwidth is given by f2 minus f2 plus f2 minus f1. So using this also you can solve for the lower and the bandwidth of 3 dB frequency shared. So the lower f1 and f2 values also. So then if we talk about next question, calculate output voltage V naught for the circuit shown. So if we just break this circuit into parts, so we have this inverting amplifier configuration, amplifier configuration, inverting amplifier configuration. Okay, and there is then in input this circuit is given. So you know how this inverting, sorry, this is non-inverting. This is non-inverting amplifier configuration. So you know how this non-inverting amplifier configuration works. Okay, so if we can solve this circuit, if we can simplify this circuit, then can we can then I think this whole solution will become this problem will become simple. So if you look only in this part of the circuit, then we have one voltage source like this, we have another voltage source like this. Okay, this is connected to the inverting terminal, and we have one 10 kilo ohm resistor here. So can we use voltage transformation, source transformation concept here? 10 volt, this is 20 volt. So if we can somehow make it like a current source, and the resistance will be the parallel combination of 10k parallel to 25k. We will have two current sources like this. The value you can easily get, that is 10 by 10k, 20 by 25k for each current source, and you will have to you will have to keep in mind the polarity also. And then we have one more resistance, that is 10k. So then finally we can add these two current sources, and these two resistances are in parallel. So finally our circuit will look like this. I'll just erase this thing. One resistor, one voltage source being connected to this op-amp. Here it is plus minus. Okay, and one feedback resistor. So it will look like this. Some V voltage, some R resistance. So you can then solve this easily. Yeah. Then the last question of the assignment. For the circuit given, if the CMR of the operation amplifier is 40 dB, so they have given CMRR is 40 dB. If we say based on the CMRR which we use normally, which op-amps which they are normally having 90 to 100 dB CMRR. So this is quite poor op-amp here, which is having only 40 dB CMRR. Okay, then the magnitude of the output voltages. So they are saying what will be the output voltage. So now if we analyze this circuit, so you know that, so if you just see the circuit, there is a bridge circuit here, the bridge like R, and the input is given to both of the input terminals of this op amp. So this is basically differential op amp, differential op amp. Okay, So we know since CMRR equals to what? 20 log AD by AC minus 20 log dB by DC. So then this will be this for 10 to the minus 40 by 20 AD by AC. Okay. Then AD we know 1 because this since this is a differential amplifier and we are having 100 1k 100 1k. So the gain will be 1 here in this case for differential amplifier or differential amplifier. Then we know, if you recall, we know V naught output voltage is given by AD VD plus AC VC. Where so AD we know we can get AC here. Uh, VC is what? V1 plus V2 by 2. This will be used here, and differential VD is V1 minus V2. So let's see what is V1 and V2. V1 and V2. So V1 will be what? Uh, these two resistors are there. It will be 10 by 2 here. Similarly for V2 also it will be what? 10 by 2. 10 by 2. Okay. So this V1 and V2 both are same. That's why V1 minus V2 will become 0. But we will have VC something. So we can get V output equals to AC VC. So we know AC, we know now VC also. We can get V naught. So and by this question, we see one more thing also, that since we were applying same input to this op amp, ideally it should not amplify that. It should give output as 0 because we are the differential gain. The differential input is 0. That is the same input V1 is V1 is equals to V2, but because of the impracticalities, because of less CMRR, it is also in like introducing a gain to this same input voltages, that is V1 and V2, and that what we saw here, that is V naught equals to ACVC. So this was all about the assignment questions. So if we see what we all so yeah, we see if we'll see what we all discussed about in today's lecture. So it was like we talked about integrated circuits. It is having miniaturized low cost electronic circuits. They are made of passive and active components. Active can be of diodes, transistors. Passives can be resistors and capacitors, and they are fabricated mostly on silicon substrate. So then the question arises, why we need ICs? Then ICs are basically, these are miniaturized versions, so we can have lots of transistors at one particular point, and then the cost is also very less because we are producing them in batches, mass batches. They are reliable, have better functionality, their speed is also high. Then we talked about ICs. Then these type of ICs, that is linear ICs, we have digital ICs. Linear, that are op amps, that is input output relation is linear. Then digital ICs, that is on or off states, they are having that is normally used in switches. Then we have IC substrate, that is silicon. The substrates are made of silicon, glass, plastic, but we normally have silicon based ICs. Then we came to op-amps. Earlier we were using only transistors. Now we came with ICs. So because of that, we were able to use op-amp, make op-amps. They were having less power, cost less, and all these advantages over transistors. Then we talked about the ideal characteristics of the op-amp, having infinite voltage gain, infinite input resistance, zero output impedance, then very high speed, very high bandwidth. Then we talked about the virtual short concept in op amps, then single-ended output and double-ended outputs. Then feedbacks in op amp, we have positive and negative feedbacks. Then then why we need negative feedback and why we need positive feedback also, that also we learned here. After that, we talked about op-amp characteristics, that is open loop gain, input impedance, output impedance, bandwidth, offset volt input, offset voltage, input bias current. Also we talked about bias current. Then we talked about differential mode gain, AD, and we talked about CMRR also. This is very important characteristics of an op-amp. Then we talk about how bias current affects the output voltage and how we can compensate that using a resistor R3, which is having a value of R1 parallel to R2. Then we talked about thermal drift, then output voltage swing and power supply rejection ratio in op amps. Then slew rate also, then how it distorts the output signal, this slew rate. Then we also talked about some filters. Like we initially realized this filter from passive components, then we made them using active filters. Then we talked about low pass filter, their characteristics, their passive component, the realization of these low pass filter using passive components and then using active components like Opamp. Then we also use variable amplifier gain Opamp in this active low pass filter. Similarly, we did this thing for second order LPF filter. Then we saw the concept of cascade voltage gain. Then we talked about high pass filter and how we can realize using op amps, and then we talked also about variable gain and high pass filter using non-inverting amplifier at the output stage. Then there was band pass filter, and by simply varying the magnitude of FC1 and FC2, there is the cutoff frequency of high pass filter and low pass filter. We can we can realize this band pass filter. Then we talked about band reject filter, where this the low pass filter frequency will be less than the high pass filter frequency. This is high pass filter. This is low pass filter. Then oscillators, more detail will see details of this we'll see in this coming weeks. But we talked about Parkhausen criteria, then the low frequency oscillators and high frequency oscillators. Then we talked about loading effects. When we are measuring voltage across some resistor, then we cannot simply connect on and this particular configuration we can measure, because it is prone to loading effect. So then how we solve this loading, we saw that using a non-inverting gain amplifier, and also we can solve this using buffer amplifier. So yeah, that was all. Thank you.